Welcome to today's class. Today we are going to study some basic hyperbolic trigonometry, by which I mean something different from trigonometry of the hyperbola. Right? So today we're going to uh, study triangles whose sides are shortest curves in the hyperbolic plane, whereas in the trigonometry of the hyperbola section, what we studied was uh, angles formed in Euclidean triangles, but where the angles were measured using the hyperbola, right? And using a Riemannian metric on the hyperbola, which was different from the Euclidean metric inherited from the Euclidean plane, right? So, but my point is that we studied angles in Euclidean triangles, right, where the measure of the angles was done in a different way. Today, what we're going to study is triangles in the actual hyperbolic plane. So today's class consists of two parts. The first part being the angle of parallelism, and the second part consisting of the cosine laws and the consequence that if two triangles in the hyperbolic plane are similar, then they are congruent, but actually congruent in a strong sense, namely that there exists an isometry taking the sides and vertices of one onto the other, right? Not only that the lengths of their sides are the same, but actually that there is an isometry taking one to the other. So let's start with the angle of parallelism. And so the basic consideration is that what one starts with the following information: a shortest curve. So let's say a complete shortest curve in the sense that it's kind of by infinite in the two possible directions. That's what I mean by a complete shortest curve. And a point outside this shortest curve. So the initial information here is the yellow information you are seeing here. Well, now red. Is the initial the input information, let's say. And so once we have this, so this shortest curve, the yellow shortest curve, and this yellow point outside that shortest curve, well, we notice that the fifth postulate of Euclid is violated because there are many shortest curves passing through this point that are parallel to the given shortest curve. Right? So here it's kind of one of them sketched, and then I can write another one, and so on. Right? So I mean, I know that my pictures are my drawings are not perfect and perhaps a bit misleading. But you see, my point is there are many, right? And actually, somehow the intuition is that you see, if one takes this point at infinity, so one of this end point of the yellow shortest curve, which lies at infinity. So it's really not in U, right? It's as I said, a point at infinity. And so it seems that you see, I mean, not it seems, this point at infinity and this finite point, they determine that a shortest curve. How do they determine it? Well, there is a unique circle that passes through this point and is orthogonal to the unit disk and passes and intersects the unit circle at this point at infinity, right? So, okay, and also kind of for the other point for the other end point of my shortest curve gamma. Oops, sorry. Right, so that there is this one and there's the original one I had drawn. They are parallel to my yellow shortest curve because the point where they meet it, the points where they meet it are not in U, right? They are points at infinity. Sorry, not in H, or not in the Poincare disk, not in D, but points at infinity, right? So first of all, so they are actually parallel to the yellow shortest curve, but not only that, one can see that they are somehow they determine a whole range of shortest curves that are parallel to the yellow one, right? So somehow that all of these that are somehow in some way intermediate to the first original two, to this one and this one, that they are all parallel, so that somehow these two determine this whole range where one can draw parallels, right? Furthermore, if you throw the shortest curve that passes through Z0 and is orthogonal to the yellow shortest curve, to gamma, and an exercise would be that such shortest curve orthogonal to the yellow one indeed exists. Then if you do that, then it's at least intuitively, at least the intuition tells us that kind of this angle should be equal to this other angle, right? So that it seems that somehow you see, so you see, if I draw only kind of half of those two geodesics, so it seems that somehow there is in all of this range. So when you draw any shortest curve whose angle with this one, sorry, whose angle, not with that one, whose angle with this orange one lies between alpha and 2 pi minus alpha, is parallel, right? So in other words, when I measure this angle, it seems that this angle, which I'm calling, whose absolute value, let's say, I'm calling alpha, determines the whole range, right? So that any shortest curve whose angle with this orange orthogonal to the yellow one lies between alpha and 2 pi minus alpha will be orthogonal, right? So such angle alpha receives the name of angle of parallelism. Okay, so it's the angle of parallelism, let's say, between or determined by the original point Z0 and the original shortest curve gamma, right? So by determined by the initial data. Okay, and of course the problem then becomes, so given gamma and given Z0, how do I determine the angle of parallelism, right? So how do I compute it? And the way one computes it is through this very beautiful theorem that says that the hyperbolic cosine of the distance from Z0 to gamma, so the distance from Z0 to gamma, where is it achieved? Well, at the point, at the point, it's the distance between z naught and the point of intersection between gamma and the shortest curve orthogonal to it passing through z naught, right? So in particular, I'm saying that there's an exercise there saying that this point of intersection is precisely the point, the closest point, the point in gamma closest to z naught. Okay, that the hyperbolic cosine of that distance times the sine of the angle of parallelism is 1, right? So this theorem tells me, okay, you can solve for alpha, right, as the arc sine of 1 over the hyperbolic cosine of A, and then see, for instance, that alpha is a differentiable function of this length, right? That in other words, that if I draw this whole ray, right, this kind of sort of half geodesic from this point to infinity, then the angle of parallelism can be put as a function of this distance, as a differentiable function of this distance, right? So in particular, for instance, one can write a program in order to later on you see write an interactive GUI where you can kind of like maybe take this one and move it around, right, with nicer pictures, right, and so on, etc. Okay, so let's prove it, or at least sketch the proof. So up to applying isometries, first of all, it suffices to prove this theorem in the upper half plane, of course. And second, it suffices to prove it in a very specific situation where the yellow shortest curve, namely my input shortest curve gamma, is actually the positive part of the imaginary axis in the complex numbers. First of all, I mean, and this should be clearer by now, right? That this is possible up to applying isometries. And second, that this point of that the point of intersection, that this point of intersection is actually in the upper half plane the complex number I. And this of course, once we know that without loss of generality, gamma is the positive part of the imaginary axis, we can apply transformation of the form multiplication by a positive number to move the intersection point around, right? So this should also be clear. And this means then that this segment of shortest curve is part of is a segment of the unit circle in the complex plane. Right? So that should be clear already. So since originally we had thrown the half geodesic that goes from z naught to this point at infinity, here it should be like an Euclideanly vertical ray, right? Because somehow this point at infinity is actually the point at infinity of C bar. Okay. So in particular, for instance, see that A then becomes the distance between I and Z naught, because it's precisely this length. Okay. Um, so let's see. Uh, we had already seen in a previous class that that this angle alpha, which remember an angle between two curves in H, or in these models U and D of the hyperbolic plane, uh, is measured by taking the angle between the tangent directions or tangent vectors um, of the curves at the point of intersection. Right? Okay, so recall that. Mm-hmm. Recall that from a previous class we had seen that that angle was actually equal to this angle. Mm-hmm. I mean, you draw the Euclidean segment from zero, joining 0 and z0, and you measure the angle it forms with the x-axis. That angle was precisely alpha, right? So this we proved in the previous class when we were computing when we were about to compute the area of a certain hyperbolic triangle. So so this means that when I draw this Euclidean triangle, the angle, this angle is 90 degrees minus alpha, right? I mean pi over 2 minus alpha, right? So that's this angle. Okay. So remember that we had at some point proved this nice formula that the okay, where you see a is the distance between the 2 points. So on top, here on top, we have the square of the norm of this difference, which is the square of the norm of this vector in R2, let's say, or in the complex plane, which that length, the length, how do we compute it? Well, we compute it with basic um, Euclidean trigonometry, because we know that how much we know how much this angle measures, the measure of this angle. So this length, well, it's of course 2 times this length, because this is an isosceles triangle. And how do we measure this length? Well, it's just the sine of this angle, which we know how to compute because this one was pi halves minus alpha. So this one is pi over 4 minus alpha divided by 2. Right? Okay, so we know how to measure this norm. So okay, so we can carry the square. This 2 is because it's this plus this, right? From the fact that this is an isosceles triangle. Okay, and these these are easily computed. This one is of course 1, and this one is sine of alpha, because we know that this angle is alpha. Okay. Right, so basic computation. And here to simplify this, I use this trigonometric identity, which I leave as an exercise for you. Sorry about that. Yeah. Okay, and now this one can be substituted by the sine of alpha, because we know that the graph of sine and the graph of cosine are very similar. So this trigonometric identity is, of course, easier to prove than this other one. Okay, and then this gives me 1 over alpha, right? So this hyperbolic cosine is 1 over the sine of alpha, which is precisely this identity. Okay, so that proves this very beautiful theorem. Exercise will prove the 2 trigonometric identities used. Right? So one is easier to prove than the other. And now we come to the cosine laws, which I would say are not easy to prove, and they are not easy to prove because one needs many non-trivial identities, and at some point, in some computations, you really have to know which identities to use. So I would say it's not easy. They are not easy to prove. It's a lot of computations. So I'm going to maybe skim over them, or try to just give an overview, a very brief overview, rather than explaining every single piece of computation, which you can anyway find in the notes, right? And so the cosine laws are these ones, this formula, and this formula for any hyperbolic triangle with finite vertices, right? That is, with internal angles that are actually positive and not 0. So the first cosine law, right? So and of course, if we write alpha, beta, and gamma for the internal triangle, for the internal angles, the notation A, B, and Z is used for the opposite sides, right? So A is the length of the side opposite to alpha, B is the length of the side opposite to beta, and same for gamma, right? So somehow the picture is something like this, right? So if this is alpha, then this hyperbolic length is A. If this one is beta, then this hyperbolic length is B, and if this one is gamma, then this hyperbolic length is C. So okay, so that's the notation, and so hyperbolic cosine is equal to product of hyperbolic cosines of the remaining two sides minus hyperbolic sines of remaining two sides, multiplied by the cosine of the opposite angle. Okay, so that's the first cosine law. Second cosine law, hyperbolic cosine of C is written in terms of the 3 internal angles this way. So the angles adjacent to C are together, and then the angle opposite to C is alone by itself, right? And everything is divided by the product of the sines of the adjacent angles to C, right? So recall that if this was C, this was, all right, at least in the picture I had from before. Okay. And so first of all, again, up to applying hyperbolic isometries, it suffices to prove the theorem in the Poincaré disk, and under the following assumptions. First, that 0 is a vertex, and actually is the vertex incident to gamma. So you see here somehow in the two laws, in the two formulas, gamma is somehow distinguished, right? Because it's the opposite angle to whatever is on the left, right? So somehow one actually has three versions of the first cosine law, 3 versions of the second cosine law, right? So okay, so 0 is a vertex, and second, one of the sides is actually horizontal, right? I mean horizontal, Euclideanly horizontal. And third, somehow the triangle opens anti-clockwise. So that those are the assumptions. If you think about it, I mean, it's clear that those assumptions are valid, are indeed valid without loss of generality, because first of all, we can indeed move one of the vertices. I mean, we can indeed move that vertex to 0. And once we are standing at 0, we can of course rotate, and then in order for this to be B, we can also, if necessary, perform some reflection. Anyway, so up to applying isometries, this configuration is a valid assumption. And then one uses, you see, some identities, which are, you see, this one is kind of is somehow similar to this one, right? Or I mean, to the general version of this one, right? Where A is the hyperbolic distance between two more arbitrarily chosen points, right? So it's kind of more looks similar to that one. Right? And then one computes, right? I mean, V alpha, this vertex, is a complex number where that you can actually write as this hyperbolic tangent of half of B. Similarly, this vertex, you can first write it this way and then rotate, right? I mean, because kind of this way is kind of it makes reference only to the length, but then you rotate, right? And you rotate by what? Well, of course, by this angle gamma. Okay. Then one uses another formula, kind of similar, I would say, in nature. And one starts computing, right? I mean, one takes this hyperbolic cosine of C. Sorry, I have not C. One uses this hyperbolic identity. This hyperbolic trigonometry identity. Okay, and then keeps going, right? And then once one uses this, one substitutes this square of hyperbolic sine using this, right? And then using this, and then in the substitution, one also uses this equality and this other equality. Okay, and then it keeps going, right? I mean, and then here one first one writes this, you pass this one here, this one here, and then one is lucky enough that actually one can also take a common denominator here, and you obtain kind of the same denominator here, so one cancels. And over here, when you pass this here, you get 1. And then you keep going, right? And at some point, you use this identity, which is kind of, once you see it, it's easy to prove, right? And then in the final step, you use this other identity that, again, once you see it, it's easy to prove, right? Using the hyperbolic cosine of the exponential. Of course, the point is once you see these identities are easy to prove. The point is, how do you know which ones are the ones you actually use, right? Anyway, and then you see at the very end, you see that the hyperbolic cosine that you were computing is equal to what you wanted to prove, right? I mean, this formula. Okay, the second cosine law. the second cosine law um, is proved using the first one. Okay. And for that, I pretty much followed the strategy of outlined in Svetlana Katok's book. I just did kind of the computations kind of to the very last consequence, right? Which in her book she says, okay, write this, this, and this, and then you notice that this is equal to hyperbolic cosine of c, but somehow she doesn't do all this computation explicitly, right? So, but one does it, and then it's kind of what one really uses. Well, one uses this identity, and actually, what one uses is that this identity allows you to write this hyperbolic sign as square root of hyperbolic cosine square minus 1. Okay, but so you see, okay, so in the notes which are posted in the website, you can go through the computations carefully, and then one arrives at you see, one arrives at like this expression is what you want, and this proves the two um, cosine laws. The point, kind of, I would say maybe the main point, is what the second cosine law tells you. So the second cosine law tells you, draw your triangle, and you see, in order to know the length of this side, all you need to know is the internal triangles, right? I mean, here everything on the right hand side is in terms is written purely in terms of the internal angles, and you can apply then the corresponding law for A and for B. And what this does is tell you that the lengths of the sides of the triangle are fully determined by the lengths of by the measures of the internal angles, right? So in particular, if two triangles are similar, so if two triangles have the same three internal angles, then they are congruent in the kind of, let's say, first of all, in the weak sense, that is that their sides that have the same length. Yeah, that's the first thing one deduces. But actually, one has not only this sort of weak congruence, that is, if the three internal angles if the internal angles of the two triangles coincide, not only do the sides measure have the same length, but actually they are congruent in a stronger sense, namely there exists an isometry, maybe orientation reversing, taking one of the triangles to the other, right? And this should be clear given what we have proved before, namely, if you have your two triangles with the same internal angles, then okay, then first of all we know that they have that the sides have the same length. Okay, but if you have you see, if you have a kind of, if you have the corresponding sides, first of all you can apply an isometry that places one side on the shortest curve determined by the corresponding side of the other triangle, right? Then you can move this one along, right? And this corresponds to being able to multiply by positive lambda in the upper half plane, right? Which is what allows us to do. Okay, until they kind of coincide. And once they coincide, if necessary, you apply maybe a reflection through that shortest curve, and after you apply that one, since the corresponding remaining sides have the same length, you must have one on top of the other. So this corollary at this point can be proved just by hand waving, because the actual technical or formal facts have been already proved. And this finishes this class and this chapter. So it was a brief chapter about area and trigonometry in the hyperbolic plane. And the next chapter is going to be Fuchsian groups. So roughly speaking, the subgroups of PSL2R that will allow us to construct hyperbolic surfaces.